Our second trend, okay, is a trend for what is called ionization energy. Now, in this word, you should recognize the base ion, okay? So what this essentially is, in short, it's the energy that it takes to form an ion. Okay? Now, in this particular case, it is a specific type of ion that we are dealing with. Okay? So when we talk about this ionization energy, we are talking specifically about the energy that it takes to remove an electron from a neutral element. Okay? So, the result of this is going to be the formation of an ion. And in this particular case, we are going to be forming cations. Okay? So, we are going to be dealing with cations. So, this is what ionization energy is. So, what we want to do is we're going to look at a specific little equation. So, if I have a lithium atom, okay, and I have a normal lithium atom where it has one electron in its highest energy level. Okay? What I'm going to do is I want to take this electron and I want to slap it with some energy. Okay? So I'm just going to give it a big old slap. So I'm taking this neutral atom that I have here, and I'm going to add energy to that. Now, the result of that is going to be when I take this electron and add energy to it, that electron is going to be released. Now, this is different than taking an electron and making it jump from a lower energy level to a higher energy level. Okay? I'm not doing that. I'm actually taking this electron and I am completely removing it from the atom, okay? So when we do ionization energy, that's a little side note that you need to know, is that electrons are completely removed from the atom, okay? Now, when you do that, what you end up with is a lithium ion that has a +1 charge, okay? Then I have this little electron that's floating around here. So I have +1 electron, okay? And that's what ionization energy does. And we can do this with any element that we want. It's just easiest with group 1 elements. But I can do the same thing to a boron atom. So a boron atom has a nucleus, okay, and it has 3 electrons. 1, 2, 3, okay? And what I can do is, with this, I can add energy, okay, to this atom. And when I do that, this electron can be stripped off. So I take boron and I add energy to it. I can make boron become a +1 charge, and then I have this 1 electron left over, so +1 electron. So one of the things with ionization energy that you need to realize is we can do it with any single element that we want, and this right here is the basic equation that we could use to write this. So here's a basic equation that we could use to write this. So without drawing all of the Bohr model stuff, okay, if I take sodium and I add energy to it, that is going to become Na with a +1 electron. Okay? So this is the equation for writing ionization energies. Okay? Now, the next thing that we're interested though then is what is the trend for ionization energies in groups and periods. So now we're going to look at group trends. Okay? So we're going to take our periodic table and we're going to look down the group and say, basically the question we're asking is, what happens to the amount of energy it takes to remove electrons as you go down a group. Okay, that's what we're looking for. What happens to the amount of energy it takes to remove electrons as you go down a group? So again, it's easiest just to take group 1 as our group. So we're going to look at what happens with group 1 elements, and we'll start with lithium. Okay, and again, it's easiest to think about these in terms of Bohr models. Okay, so lithium has 1 electron in that first energy level. Okay, sodium, shoot, I wanted blue, sorry. Sodium has 3 energy levels, and it has an electron. And I'm going to go one more. We're going to go potassium has 4 energy levels, 1, 2, 3, 4, and it has 1 electron in the 4th level. So, when we start looking at the energy that it takes, okay, one of the things that we can look at here is what is happening with the shielding effect. Okay, in one of our previous lessons, we talked about the shielding effect. And if you start looking at this, the shielding effect essentially affects attraction. So this affects attraction between electrons and protons. So this electron out here, okay, is being attracted to the nucleus right there. Okay? But so is this electron, okay, and so is this electron. Except as I go down the group here, what do you think is happening to that attraction? Okay, and because of the shielding effect, one of the things that happens is as you go down the group, the electrons become less attracted to the nucleus. Okay? So what do you think that that's going to mean for removing them? Will that make them easier to remove or harder to remove? And the result of that is it essentially makes electrons easier to remove. Okay? So as I go down a group, okay, there's a couple of different things that are in play here. Number one, our electrons are getting further away from the nucleus. Okay? And so they're getting less attracted. And then number two, we have more and more shields happening. Okay, so we have more shielding from the nucleus. So it's going to be easier to remove electrons from potassium than it is going to be to remove electrons from lithium. So when we start talking about our trend ends up being then down a group, so I'm going to put trend group, our group trend, is that the ionization energy Sorry about this. Then I change colors. The ionization energy decreases down a group. Okay, so that is the group trend, that the ionization energy decreases down a group. And this right here is the reason. Remember, I always want a reason. This is the reason. As you go down the group, the electrons become less attracted to the nucleus, making them easier to remove. Okay? Now, that is something that we can see when we look at actual numbers. So this is first ionization energies of some elements. And as I look down just group 1, you can see we start out 1,300, and as I go down the group, my ionization energy gets less and less. Don't worry so much about what the numbers are. These are all kilojoules. Okay? So the same thing that when we were dealing with Q equals MC delta T, we had joules as our units, okay? But we're not going to get into that again. But we're interested in the trend. So we start at 900, we end at 500, okay? The trend is that we get smaller, and that happens all the way along. Look at group 13, we get smaller. Look at group 18, we get smaller. Okay, and that's pretty much any group along the way. Our trend is to get smaller. Okay, so we look at these specific trends, and that's what we go for. Now, you start looking in here. Okay, you're going to see some anomalies. That's okay. Like here, right here, we get bigger. Okay, and here we get bigger, but that's okay. I'm not worried about overall. I'm worried about overall what the trends are. Okay, so that's some of our first trends. Okay, as we look at ionization energy. Now we want to look at the period trend. Okay, what happens as we go across a period? So again, we're going to take period 2, okay, where we can look at lithium, beryllium, boron, carbon, oxygen, nitrogen. Oops, I have those two backwards. Carbon, nitrogen, oxygen, fluorine, neon. Okay, so we can look across there. And again, if you remember, okay, when we talked about atomic radius, okay, as we go across, we only have 2 energy levels, but these atoms started getting smaller and smaller as we went across. Okay, so atomic size is actually going to have a lot to do with this, because if you remember, there is greater attraction for electrons over here. Okay, there's a large attraction for electrons there, and there's less attraction for electrons here. Okay, well, if you just think about that, if I'm over down at this end with neon, and there's a large attraction for the electrons, then I'm not going to be able to give up electrons very easily. In fact, if you even think about it even more, what would things like fluorine rather do? Fluorine would rather gain electrons, okay, and not lose them. So fluorine wants to hold all of its electrons that it can. Okay, fluorine wants to keep those electrons. So does oxygen. So does nitrogen. Neon is already happy. It doesn't want to give up any of its electrons. So over here, on this end, if I want to take away an electron, I'm going to have to add a very large amount of energy. Okay? So even if you look at this periodic table then, we start down here with lithium at 520, but then look, we go 900, drop a little, 800, but 1,000, 14, 13, 16, 2,000. Okay? So with this, our period trend is that we increase in energy to remove electrons as you move left to right. Okay? Across the period. Okay? So that's the period trend, is that we increase. And again, I always want a reason. And in this case, our reason is group 17, 18 elements have greater attraction for electrons. So larger groups numbers, I'm just going to put that, larger group numbers have greater attraction for electrons. Okay? So, larger group numbers have greater attraction for their electrons. All right? So that is our period trend. So again, looking at this picture, oops. Okay? You can see the trends in pretty much every row. Period 3, start low, end high. Okay? Period 4, start low, go across here, and end high. So, if you remember that periodic table, summary periodic table that we made, okay? So, we made a summary periodic table earlier. We have atomic radius here, and atomic radius here. Now we're going to add ionization energy. And ionization energy increases as we go down. And now we're going to put ionization energy here. Excuse me, I did that backwards. Dang it, sorry. Ionization energy decreases and ionization energy is going to increase here. Sorry about that. Okay? So, hopefully you're making your table neater. Now, there's a few terminology things that we need to talk about with ionization energy. So, with ionization energy, where did that go? Oops, I apologize for this. I don't know where it went because I'm going all over. There is something called first ionization energy. Okay, and that is the energy that it takes to remove the first electron. However, if you have an atom that has multiple electrons, you can have multiple ionization energies. Okay, so second ionization energy is just the energy required to remove the second electron. This is where you're going to want to pause because I'm just going to go quickly through this. And yeah, you can write all that down as well. And if you start looking at these things, okay, this is first, second, third, and fourth ionization energies of 3 different elements: sodium, magnesium, and aluminum. And one of the things that you should look at is that these are in period 3. Okay, so sodium, okay, to lose its first electron because it's a group 1 element doesn't take much. But now to lose its second, notice the big jump. And the reason for that big jump is because it was stable at this point. Okay? And it did not want to lose that next electron. It reached stability. If you look at magnesium, this is its first electron, this is its second electron. Okay? And maybe if I look at, go this way, this is a 3s1, so this is losing that 3s1. Magnesium, this is a 3s2. This is the first electron, that's the second electron. Now, when we lose those two, okay, we're a noble gas, and we don't want to lose that third one. And then aluminum doesn't take much to lose the first, second, or third, but there's a big jump to lose the fourth electron. Okay? So that's different ionization energies. So basically what I'm telling you is you could essentially remove all electrons from all atoms if you have enough energy. So maybe we want to write that down. It is possible to remove all electrons from all atoms if you have enough energy. Now, I don't believe that that's ever been done, okay? So essentially what we're saying is you can have an Fe plus 26. You could remove all of its electrons, but we don't ever do that, okay? And because I think it would just take way too much energy. So even though this is possible, it never happens, okay? And this is just another chart of first, second, third, fourth, fifth, sixth, and seventh ionization energies for period 2 elements. Okay? All right, there's one last thing. Okay? There are 4 factors that affect ionization energy. The first one is nuclear charge. Nuclear charge is really number of protons. The larger the number of protons, the greater the ionization energy. Second, shielding effect. Okay, I said earlier that this is going to be an answer to a lot of your questions. The greater the shielding effect, the less the ionization energy. Third one, radius. The greater the distance, the less the ionization energy. And the last one is sublevel. An electron from a full or half full sublevel requires additional energy. So, again, I know there's a lot there. If you need to pause, pause.